And we're back. Welcome back and happy Thursday. Today we'll switch gears and begin a new module concerning main memory. But before we begin, a few administrative bits. There is additional reading in place by the 12th of November. Please make sure you've gone through sections 9.1 through 9.3. That's pages 349 to 371. So at this juncture, this week, of course, we have 6 weeks remaining, and some milestones to note. Written exam number 2 will be the week of the 16th of November. The last day of classes will be Thursday, the 3rd of December. Reading day will be Friday, the 4th of December. Our scheduled final exam period for this class will be the 10th of December, which is a Thursday, between the hours of 10:30 and 12:30 p.m., 10:30 a.m., 12:30 p.m. And during this time, we will be scheduling our final project presentations. The last day of finals is also when the final project reports are due. So the presentations will be on Thursday, the 10th of December, and the projects themselves will be due on the 11th of December at 8 p.m. So please mark down on your calendar these key milestones. All right, so the objective of the Chapter 9 on main memory is to provide a description of various ways of organizing your memory hardware. Now, there's a relationship between the memory hardware on your machine and the software, i.e. the program itself that's executing after it's been loaded into main memory. So we'll also, for Chapter 9, discuss various memory management techniques and include concepts of paging and segmentation. Okay, so let's look at this address binding. And so a program has to be brought from disk, and it's just a program, and it doesn't become a process, a unit of execution, i.e. the execution of an instruction stream. It doesn't become a process until it's loaded into memory and placed within a process structure so that it can be scheduled by the short-term scheduler, and it can be run. And so main memory and registers are the only types of storage mechanism that the CPU can directly access because that's on board the CPU. Again, we said the CPU consists of a number of components: the arithmetic logic unit, the floating point unit, we have the register file, we have the stack pointer, we have the program counter, and we have the instruction cache, and we have the data cache. We also have main memory, the subject of Chapter 9, and we also have our disk on which our programs are stored. And of course, in a von Neumann architecture, they're all interconnected by a high-speed bus, and certainly the disk is arbitrated by the I/O controller, which maintains a buffer on behalf of this device, namely the disk device. Okay, so we have our program sitting on disk, and when you run this program, it's loaded into memory. So here's your program loaded into memory, and then parts of that program, both its instructions and data, are loaded into the data cache and to the instruction cache. And so the main memory is accessed by the CPU directly, and the registers are accessed by the CPU. So the CPU also maintains memory pointers, so it can access locations or address locations in memory for which to load blocks of data. So the memory unit only sees a stream of addresses and read requests or addresses and data for write requests. And so this memory device here, it knows that, okay, well, I'm getting a read request. I have an address and I have an amount of data and it satisfies this request by sending data to that particular device that issued the request. Likewise, for the write request, the CPU specifies some amount of data and an address and here's your data, and that's sent to the memory device, which then writes that data at the specified address. And so that's what the memory unit sees. It sees a stream of requests and addresses, and it sees a stream of addresses, data, and the write request. And that's all your memory device sees. And so register access is in one CPU clock cycle. And so it's really, really fast. The CPU doesn't go off chip when it's going to read information from its register to set up an instruction. That if you have a 3 gigahertz CPU, that's 3 times 10 to the minus 9, or 1 nanosecond of time. It's really, really small for the access to that register, 1 clock cycle or less. And so main memory, on the flip side, if we look at our von Neumann architecture, main memory requires going over the bus to address this memory from this memory device and to get this data or to write data. And so that can take more than 1 clock cycle from the perspective of the CPU for multiple reasons. It has to set up the address. It has to initiate the transaction by sending the request and or the buffer full of data. It also has to send all of that information back and forth across the system bus, which operates at a slower speed than the CPU. Okay, and so because of that memory taking many cycles, this can cause what's called a stall cycle. That means that the CPU is slow in its performance because it has to wait for the memory to respond to its request. For this reason, we have a cache, the instruction cache and the data cache, that sits in between your main memory and your CPU registers. And so if we look at this, the reason for the instruction cache and the data cache is so that we load blocks of instructions and blocks of data so that the CPU minimizes this stall. Now, certainly, if the CPU accesses a piece of an instruction, that's the last instruction in the instruction cache, the next access, it's going to require the CPU to load another block worth of instructions into the instruction cache. So it still has a memory stall, but from one instruction to the next, you don't get these memory stalls. So the whole purpose of the instruction cache and the data cache is to minimize or reduce the number of memory stalls, i.e. the number of times the CPU has to wait for memory to respond. Okay, and so the protection of memory is really, really important so that you don't have the data and the code of different programs overwriting one another. And so the protection of memory is required then to keep all the different parts of your program, code, and data for the different programs separated from one another so they're not being running over each other. And so this idea of protection is important for correct operation of your programs. And so one method for doing this is with so-called base and limit registers, and these define the beginning and the amount of memory from that beginning address or location that define where your program sits. And so the CPU then, for every address it generates, when it generates addresses for read requests or write requests from memory, done in user mode, it has to make sure that each one of those addresses lies in that region of memory, that block of memory, within that particular bounds specified starting at the base address and going as far as what the limit register holds. And so here, in this example, we have memory, and we have different processes. You can imagine this is process P1, process P2, process P3. And process P2 is associated with a number of addresses. Well, the base register is going to hold for process P2 in this example the starting location of memory where process P2 was loaded, and the limit register holds the number of bytes that process P2 will occupy relative to this base. So if we take this 300,040 and we add the 120,900 bytes, we get an ending address for process P3 of 420,940. And so the base register is where memory starts, that address, and limit is how many bytes wide this block is. And so this particular block is 120,900 bytes long. And so at the end of it, well, that's 120,900 plus the 300,040, that's 42940 is the ending address where process P2 ends. Okay, so the hardware address protection occurs by checking whether or not one of these read or write request addresses generated by the CPU violates this block for the particular process defined by the base and limit registers. And so the CPU generates a stream of addresses. It checks the base register to see is that address generated greater than or equal to the base address. If it's no, it traps the operating system, and you raise an error that you are trying to violate or access memory that does not belong to you, you being the process. If it is greater than or equal to the base register, it then checks to see if it's less than the address defined by base plus limit. If it is not, then you trap to the operating system again, so you've exceeded it. If it is, then you go ahead and you get that address associated with the program. And that transaction, whether it's a read or write transaction with memory, between memory and the CPU, is allowed to proceed. And so another thing that happens is so-called address binding. We said that a program initially is stored on disk. Here's your program. And that program, when you instantiate it, it's loaded into memory. And so that program is loaded off disk and it sits in memory. Now, a key question is where exactly do you load this program when you take it off a disk? Well, we said that memory consists of a bunch of addresses, address location 0, 1, 2, 3, and so forth. Now, there needs to be a scheme to associate instructions by their position within the instruction stream with the location where that program exists in memory. Because when the CPU tries to read these instructions or read this data, it needs to have an address of where it is in memory. But when your program is executing, well, your program says there's the first instruction, here's the second instruction, there's a third instruction, and so forth. So to your program, you have a bunch of instructions. There's the first instruction, second instruction, third instruction, etc., up to some maximum instruction, kth instruction. And so programs on disk that are ready to be brought into memory to execute form an input queue. And so you have programs that are lined up, they join a queue, program 1, program 2, etc., program N. And in this queue, they occupy position and they're staged for loading into memory. And so without any support for figuring out how to load them into memory, they're all going to have to be loaded at address 0. Because if you're going to start out, well, you might as well have it at address 0. But it's not convenient to have the first process loaded always at physical address 0. Because if you have more than one process, so let me redraw memory, and you have process 1, program 1 loaded as process P1, and now you have program 2 that's in the queue ready to be loaded, well, you can't load it in memory location 0 because there's something already there. So it can't be convenient to always load the first process at physical address at 0. Sometimes you want to load it other places. And by the way, there's already a process sitting there at address 0. That's your operating system. And oftentimes when you see memory drawn in the book, it's drawn so that the low addresses are at the bottom, 0, and the high addresses are at the top. And the operating system is always occupying starting at address 0, and technically it's the bootloader that runs in the beginning. Okay, and so it's not practical to have the first user process to always be loaded at address 0, so we need some support to translate or map these physical locations within the program for instructions in its instruction stream to map that to memory addresses in memory when it's loaded. And so addresses are represented in different ways at different points in the execution of a program. And so typically when you're dealing with source code, you usually deal with so-called symbols. So you have functions like copy, functions like memset. You have names for variables like int cursor. Cursor is a symbol. Copy is a symbol, and it's a name. And that name is used to refer to some location in your program. So copy, maybe you have a function called copy, open curly brace, close curly brace, and here's the implementation. So when you use the symbol copy, you're referring to that particular instruction. Maybe it's not the first instruction, it's the second instruction, that particular instruction in your program. And so programs deal with symbols. Those are names. But when you compile your code through the compiler, one of the things that happens is that these names are bound, all the addresses or locations in your code are bound to so-called relocatable address. And what a relocatable address does is it refers to all locations of instructions in your program. You can think of it as an address in your program. It's not really an address. Let's just call them locations. You can think of it as all of the locations in your program being described as relative to the starting location, location 1 in your program. So the next location is called 2, the next location is called 3, an arbitrary ith location in your program. So that's how locations of instructions are referred to in your program. Now this relocatable part says that now I can take my program, here's my memory, and I load that program into memory. It doesn't matter if I put it here or if I put it in a different location in the program. I can relocate this program, and the first instruction offset from the beginning of the program, and the second instruction offset at the beginning of the program, and the ith instruction from the beginning of the program, they still remain the same in their relative position. And so what this relocatable address means is that it doesn't matter where in memory your program is placed, the particular location within a program of an instruction is always the same. And so whenever you link your program, the linker is pasting together all the executables and object files together with the system libraries, and the loader then binds the relocatable address to an absolute address. So how does that happen? Well, we'll talk about that. But each binding is the association of this relative location with a physical location in memory. And so programs deal with relative location for your instruction. And once it's loaded into memory, each relative location is mapped or bound to a physical location. And each binding action that happens maps from this addressing or this identification of instructions in this logical view from your program to this physical view in your memory. Okay, so let's take a look at this logical addressing in a program for identifying instruction locations versus the physical addressing of these instructions once they're loaded into memory. And so the concept of a logical address space is bound to a separate physical address space. This binding is central to the proper function of memory management. So a logical address is generated by the CPU. That's also called the so-called virtual address. So the CPU says instruction number 1, instruction number 2, instruction number 3, and so forth. And a physical address is what is seen by the memory unit. So the CPU sends logical addresses to the memory device, and specifically associated with the memory device is a memory controller. And this memory controller translates this logical address into a physical address in memory. And so all physical addresses are generated by a program as a result of the CPU's access of a logical address or virtual address. Okay, And so this logical virtual address is a program's identification of locations in a program, but the physical address is this identification of where in memory that piece of the program or that instruction has been loaded. And so logical address space is a set of all logical addresses generated by a program, and the physical address space is a set of all physical addresses to which those logical addresses have been mapped that are generated by the program. So physical is the result of a mapping operation. So let's take a look at the memory management unit, and we'll look at the memory controller. And so the memory management unit, or MMU, is a device at runtime, and that's important. It runs at full speed as the addresses, logical addresses, are generated by the CPU. At runtime, it maps each of those logical addresses or virtual addresses to a physical address. And there are many different approaches for how this is accomplished, and that's what the subject is for Chapter 9. And so to start, let's think about a simple way where the value of a so-called relocation register is added to every address generated in the logical address space. And so what that means is, we said the program refers to its addresses, its logical addresses, as instruction 1, instruction 2, etc., through some ith instruction out of, say, n many instructions. And that program is loaded into memory. So here's memory. And if that program is loaded, let's say at address 1000, well, that program has instructions that are the first instruction, which is at address 1000, the second, the ith instruction up through the nth instruction. Now, of course, if we take this so-called relocation register, that relocation register really just describes where in memory that particular program's beginning instruction was loaded. And so here we have our program. If that program was n many instructions long, and it was loaded so that it starts at memory location 1000, that means if we take that 1000, add it to 1, it's now 1001. And this next one is 1002. And this next one, ith instruction, is now 1000 plus I. And so if we decide to take our program and load it somewhere else in memory, say at address 2000, well, we just add 2000 to each one of these logical addresses, and we can now pick this program up and move it in memory. We can relocate it. And so the relocation register, in our simplest approach, is added to every address, logical address, by a user process at the time it's sent to memory. So when you load it off disk into memory, that's when you add the relocation register to each one of the logical addresses to get the physical address where that program resides. And so the base register, as it used to be called, is now called a relocation register. And in the old days, MS-DOS on the Intel architecture, it had 4 location registers called AX, BX, CX, and DX. Sometimes they were called segment registers. And I remember these very well. So the user program will deal solely with logical addresses. It never sees the physical address. It generates a logical address, and this relocation system is used to map to a physical address. And so this execution time binding occurs whenever a reference is made to any location in memory. So that could be a variable name. It could be a function name. And a logical address is bound to a physical address. This happens at runtime, so it's going very, very fast. So in the beginning, this relocation is dynamic, and dynamic uses the relocation register. Initially, a function or routine, which is a block of instruction, is not loaded until it's actually called. And this gives you a lot better utilization of memory, because why load something into memory to take up space if you're not going to use that function all the time? And so all the routines are kept on disk and stored in a relocatable format. And then it's once you call the function, is the code for that function loaded into memory, and then the relocation address comes into play as you're generating logical addresses. And so in this example, and this is in the book, you have a logical address, say address offset 346, and you go to the memory management unit, that's the memory controller, and it has a relocation register, for example, of 140,000, 14,000, and you add that 14,000 to the 346, the physical address is 14,346. So in that particular case, your program was loaded starting at address 14,000, and now instruction number 346 in that program is mapped to address 14,346. So the 14,000 is the location register. And all of that is done by the memory management unit. Sometimes it's called the memory controller. Okay, and so this is useful when you have a large body of code and you need to handle parts of it that are infrequently used. So let's say you have 100 functions, 200 functions. Take a spreadsheet, for example, or take a word processor. It's not all the time you're going to be using spell check. So why have memory occupied by the block of code in your instruction stream corresponding to the spell check function? That's a lot of code to implement spell check. So this requires no special support from the operating system. It's implemented through the program design, but the operating system can often have libraries to help you implement this dynamic loading. And so this is something that in the hardware level, operating system can make it easier, but it's just the design of your program, the logical addresses that drives this process. The relocation hardware does all of this mapping for you. And so there's different types of linking, and we talked about it when we talked about the linking stage after compilation. There's so-called static linking, and in static linking, your system libraries and program code are combined, pasted together by the loader into a binary form or image of your program. With dynamic linking, this is not the case. The linking is postponed until execution time. A small piece of code called a stub knows where to find the actual library routine, and it goes and fetches it when you try to access that function, and the stub replaces itself, overloading itself, rewriting with the address of the routine, and executes that routine. And so this saves you from having all parts of your system libraries loaded into memory, which can be very large, and you only load them when you need to actually use them. And so the operating system then checks if the routine is in the process's memory space. If it's not in the address space, it adds it to the address space. And dynamic linking is particularly useful for libraries when you want to extend the capabilities of your program with a bunch of modules, and sometimes, at least on the Unix platform, they're called shared libraries. And the Windows program is called a dynamic link library, or DLL. Shared library or shared object is often called SO file for shared object. And so this is very applicable when you want to patch a system library, right? You have different versions of libraries and you just swap them out, you get them dynamically loaded, and all of a sudden you can use a new library. Okay, so let's take a look at this idea of bringing in the program from disk into memory. It's called swapping. And so a process can be swapped or brought into memory from disk, but it can also be evicted or kicked out of memory and temporarily sent to a special part of your disk called a backing store. And the reason for doing this is to save memory. If all of the programs that you want to run cannot physically fit in main memory, then some of them that you aren't using are kept on disk temporarily and brought back in when they need to execute again. And so this occurs if the total memory space of a process exceeds the amount of physical memory. So let's say you have main memory, and let's assume that main memory is big enough to fit, let's say, 2 processes. Now you have disk, and let's say you have a bunch of programs. You have Microsoft Word, MSWD. You have maybe Firefox browser, and then let's say you have a email or Dropbox. Okay, so now you run Firefox it's loaded. You run Dropbox, it's loaded. And now all of a sudden you want to run MS Word. Well, what happens? You can't fit it. So that means you're going to unload Dropbox process temporarily into memory in a special part of your disk. And that special part of your disk is separate from where you store your programs. So maybe in the top part of your disk, we store programs. And in the bottom part, we store those process execution contacts, that executable form of your process. Instead of being resident on main memory, we're going to store them in that special part of disk. That special part of disk is called the backing store. So this backing store kind of acts like the memory resident form, but it's not in memory. It's actually on a special region of disk. And if you ever install a Linux distribution, one of the things that it asks you is to format your swap partition. Now, the rule of thumb is that your swap partition should be 2 times the amount of memory that you have on your system, up to a certain point. And so this swapping is using of a special part of disk called the backing store to temporarily store the process form of your program, the executable form, on disk, because they can't all fit into memory. So once Dropbox is swapped back out, then Word is run, and then Word is run for a little bit. Word might be swapped out, so Word swapped out, and Dropbox is swapped and loaded back into memory. And so this has its drawbacks because disk is slower than memory because you have to initiate an I/O transaction. And you'll notice sometimes if you run a lot of programs on your machine, at some point it'll slow down tremendously and your disk will start going crazy. And that's because you're now swapping in and swapping out a lot of programs. And so this backing store is a fast disk and a region of your disk, and it's large enough to accommodate copies of all of the in-memory form, the memory image, for all of the processes and users that are on your system. And so it must provide direct access to these memory images on the disk. And so the format of your program in memory is the same as its format on disk. It's just the medium used to store it is different. It's disk instead of memory. And that's called your backing store. And so in certain systems, there's a variant of swapping called rollout and roll-in, and it's associated with different prioritization if you associate them with your processes. If you have a lower priority process, that's swapped out of memory onto the backing store and replaced with a higher priority process that's on the backing store so it can be loaded and executed. And so this rollout and roll-in is driven by the process priorities, but it's still swapping. And so a major part of the time it takes to swap is the transfer time. That's the time it takes to take that data for your process executable state, to read it off the disk, the backing store, to load it into memory, right, across the bus and into RAM. Now, it's a bulk data transfer through direct memory access, but nonetheless, it's going to traverse the bus. So it's going to take some time to do that. And so the total transfer time then is directly a result or a function or proportional to the amount of memory that's swapped. A bigger program is going to take longer to swap into memory from backing store and to swap out of memory to the backing store. And so the system is going to maintain, as we said, the ready queue of the ready-to-run processes that have memory images on disk, right? That's the medium-term scheduler. And this ready queue is going to not be those that are in memory, but those that are stored in the backing store. So we have the usual ready queue that we had for processes that are ready to run, and then we have a ready queue for on-disk memory images that are loaded into memory. So one question that one might ask, does a swapped out process need to swap back in to the same physical address? So if you have your main memory and you have some process, P1, and let's say P1 is loaded at address 100. Now you swap it out onto the backing store. When you swap it back in, do you need to reload it back in the same place? Well, that depends on the method you use for binding. So if you have some I/O requests that the process is waiting for memory space. Well, if you have a pending I/O request, you don't want to swap it to a different location because that I/O request is going to result in some buffer being filled. Now, what happens if you're in a new location when you swap back in? Well, that disk I/O, it knows I'm going to do the direct memory access transfer to that location, so something bad will happen. So you have to consider any pending I/O requests to or from the process in memory space to determine whether or not you're going to bind this process to the same location when it's loaded from the backing store. And so there are different versions of swapping that are found on the major operating system platforms, Unix, Linux, and Windows. Swapping typically is normally disabled. It's not swapping, and it's started once a certain amount of memory has been allocated. Now, that's a tunable parameter that you can tune for your kernel parameters, but nonetheless, swapping doesn't normally happen until a certain amount of memory has been allocated. So if you're running new programs and have a lot of programs sitting in the background, and all of a sudden you notice your system starts to get really, really slow, that's because swapping is starting to happen. So that means you need to exit some of your programs so that you don't have the degree of multi-programming so high. And so the swapping then is disabled once again. The load on memory, the demand for memory, falls back below that threshold. And so swapping impacts the context switch time, because if you're going to context switch from one process to another, but that other process is on the backing store, in addition to that dispatcher action, you're going to pay the cost of that time it takes to swap it from the backing store back into memory. And so this is a schematic view, and it's in the book, of the swapping process. You have a process P1 that's resident in memory. It gets swapped out, written to the backing store. And again, it's really, really important to note that the backing store is different from where the program executables are stored, right? They're two separate parts of disk. It could be a separate disk. It could be a partition or a region of a disk set aside for that purpose. But nonetheless, we have a process P1 in memory. We swap it out. It's now in the backing store. Process P2 is selected. It's swapped in to memory, so here's process P2. And so this backing store is like an additional piece of memory. It's slower, albeit, but it's used to store the executable image of the process. And so this version of process P1 in the backing store is not the same as this program version of that process. Program1.exe is the program on disk, but it's a process. It's a different form when it's in this memory image format in the backing store. Okay, really, really important distinction to remember. All right, so there's swapping, and with that, we'll end there. Again, please make sure you're staying on top of the reading, and as usual, have a great weekend, stay healthy, stay safe, and I will see you all